Hello everyone, this is Vasishta from Aerobie section. Today I am going to explain about thermal stresses in simple bars. So, coming to the topic, thermal stresses are due to the change in temperature of the component, and the component is mechanically restrained to expand or contract. Conditions for the existence of a thermal stress: there should be temperature change in the component. The thermal expansion and contraction should be restricted either completely or partially. When the temperature of an object changes, its dimensions are changed, which results in strain. If alpha is a quotient of thermal expansion, the uniform thermal strain is given by strain is equal to into temperature delta T, alpha into delta T. So as we can see, the temperature, the thermal stresses, so the temperature is the main thing which acts on the thermal stresses. Next, thermal effects: change in temperature produce expansion or contraction of material and result in thermal strains and thermal stresses. For most structural materials, thermal strain is proportional to temperature change. Thermal strain is equal to the proportional of a temperature change, that is sigma T is equal to alpha proportional to delta T. The coefficient of thermal expansion is alpha. When a sign convention is needed for thermal strain, we usually assume that expansion is positive and contraction is negative. Thermal stress: suppose we have a bar subjected to an axial load. We will then have sigma is equal to nu is equal to sigma by E. Also, suppose that we have an identical bar subjected to a temperature change delta T. We will we will then have epsilon r is equal to alpha into delta T. Equating the above two strains, we will get sigma is equal to E into alpha into delta T. We have we now have a relation between axial stress and change in temperature. By assuming that the material is homogeneous and isotropic, and then the temperature increase delta T is uniform throughout the block, we can calculate the increase in any dimension of that block by multiplying the original dimension by the thermal strain, where delta R is equal to epsilon into R into L, that is equal to alpha into delta T into L, where temperature minus displacement relation. As we can see in this diagram, block of material subjected to an increase in temperature. Thermal strain: as in a case of lateral strains, thermal strain does not induce stresses unless they are constrained. The total strain in a body experiencing thermal stress may be divided into two components: strain due to stress epsilon, and the due to temperature epsilon T, that epsilon is equal to epsilon sigma plus epsilon temperature, stress temperature, that is equal to sigma by E plus alpha into T. Thermal stresses in bars in tampering sections. Take a circular bar uniformly tapering which has L is equal to length of bar, D1 is equal to diameter of bigger end of bar, and D2 is equal to diameter of smaller end of bar. T is equal to change in temperature, alpha is equal to coefficient of thermal expansion. As we can see in this diagram, deriving the equation of a thermal stress for tapered section. Due to contraction compressive force P acted when temperature will be rise, delta L is equal to 4PL by pi into E into D1 D2. Due to expansion, the temperature will be rising. That time delta L is equal to L into alpha into T. Here no change in length in equation 1 and 2. 4PL, now we have to equate them, so that the 4PL by pi d d1 d2 is equal to L into alpha into T, that is equal to P is equal to L into alpha into T into pi into E into d1 d2 by 4L. where sigma is alpha T into E into d1 by d2. That is the maximum stress we get. Now, thermal stress in bars of varying section. From Hooke's law, that stress by strain is equal to sigma by E, that is equal to P by A into E. From the definition of strain, delta is equal, epsilon is equal to sigma delta by L. That equating and solving for the deformation, delta is equal to PL by AE with variation loading cross section or material properties. Delta is equal to sigma summation of PI by AIEI. As we can see, there is an example regarding the thermal stress in the body. That E is equal to 29 to 10 power minus 6 psi. We have to determine the deformation of a steel rod with a given loads. That divide the rod into components at a load application, apply a free body analysis on each component to determine the internal force. Evaluate the total of the component deflections. Now, solution. Divide the rod into three components. That is A, B, C, D. From that, Ln is equal to area is equal to, then applying the free body analysis to each component to determine internal forces. P1 is equal to P2, P1, P2, P3. P1 is equal to 60 into 10 power 3 lb minus 15 into 10 power 3 lb 30 into 10 power 3 lb. With evaluating deflections, we get strain delta. Now, temperature stress in composite bars. As we can see that, as we can see in this solution, we have 30 kilopascals and 45 kilopascals and 75 kilopascals are, this is the load acting on it with a 12 inches and 16 inches. From that, as we can see, it is divided into three parts with a 30 kilopascals and a 30 plus 40 kilopascals and 30 plus 45 plus 75 kilopascals. We get different types of free body analysis with the delta is equal to summation of pi li by ai ei. That is equal to, if we take 1 by e as common, p1 l1 by a1 plus p2 l2 by a2 plus p3 l3 by a3. Now we get E is equal to 29 into 10 power 6, that is the value we have got, and the area for A1 and A2 will be same, and A3 is different because of the smaller section. Now we got the value in inches. That's the total deflection we have occurred and we have come through. And as we can see in these diagrams, we have temperature stresses in composite bars. In composite bars, we have alpha 1 and alpha 2 in this A diagram. And if we stretch that 1 and 2, we get L into alpha 1 into T plus L into alpha 2 into T, where FL by A1 E1. And in this, the temperature stresses for these composite bars can also be seen. And temperature stresses continue. Free expansion in bar 1 and bar 2 are L into alpha 1 into T and L into alpha 2 into T respectively. Due to end fixing forces, a force that decrease in the length of bar L is FL by A1 E1 and the increase in length of 2 is FL by A2 E2. At equilibrium, L into alpha 1 T minus FL by A1 E1 is equal to L into alpha T into T plus FL by A2 E2, that is F into 1 by A1 E1 plus A2 E2, that is equal to T into alpha 1 minus alpha 2. Sigma 1 is equal to T into alpha 1 minus alpha 2 into A2 into E1 E2 by A1 E2 plus A2 E2. And sigma 2 is equal to T into alpha 1 minus alpha 2 into A1 into E1 into E2 by A1 E1 plus A2 E2. As a result of force, F will be compressed while 2 for bar 1 will be compression while 2 will be in tension. So this is about the, and as we know that thermostat thermostat is an example and application of an this thermal stresses. And this is all my explanation about thermal stresses in simple bars. Thank you.